So this talk is about the question of whether machine learning can discover the laws of nature. And it is based on a recent NeurIPS paper that we published. And I encourage you, those who are interested in the more technical parts, to read the NeurIPS paper. But my plan for this session is to actually talk more about the big picture, and specifically a question that I've been interested in for many years, and I'll give you a spoiler, we're not going to answer in this session, of whether machine learning can be used for scientific discovery. So not like we often use machine learning in order to predict or find anomalous events. Can we really use it to discover laws of science? In the first part of the talk, I'll talk about some unwarranted optimism about the use of deep generative models in this setting. And then I'll talk about our results, which, so the first half will be pessimistic. I'll show how certain things don't really work as advertised. But in the second half, I'll try to give some more optimism and talk about how we can really use a different type of machine learning to discover scientific knowledge, and I'll show some experiments. So let me start maybe by talking about one of the first data scientists, and that's Johann Kepler. And the reason I call Kepler a data scientist is because when you talk about many scientists or astrophysicists, they often both do experiments, then they try to analyze the data, go back to doing experiments, analyze the data again. Kepler was an interesting case because he only analyzed other people's data. In that sense, he really was a data scientist. So let me read this quote from an introductory text on Kepler. When Brahe suddenly died in 1601, all of his data was given to Johann Kepler, and it became his responsibility to finish Tycho Brahe's work. For the next 11 years, Kepler investigated mathematical patterns in the data, making and testing hypotheses until he developed an even better understanding of the arrangement and movement of our solar system than anything that had gone before. So this is really, I think, a triumph of data science, in that we have this genius who just sat there, analyzed the data, investigated mathematical patterns, and somehow figured out something about the way the world works. In modern terms, and what we would say that Kepler did is nonlinear dimensionality reduction. So let me try to make that mapping. If we think of some measurements x, which are very high dimensional, say the motion, xi is the motion of planet I, and just think of this as a very long vector, the motion of every planet on every day. So we'd have thousands of measurements per planet over many years. And then when we do dimensionality reduction, we think that this high dimensional vector is actually a function of a low dimensional latent variable, which I'll denote by Ci. And we try to figure out the mapping from the latent variable Ci to the high dimensional measurement Xi. So in that sense, if you look, say, at the Ptolemaic method of model of how the solar system works, in which the Earth was at the center and the planets rotated around the Earth, that was also a form of nonlinear dimensionality reduction. But in this case, the latent dimension was 2. So in the Ptolemaic method, every planet was defined by 2 numbers, the radius around the Earth and the secondary radius around it. And those 2 numbers determined the motion of the planets. Whereas in the Galilean method, which was based on circles around the sun, it's a single number. The distance from the sun was the one that measured, determined the motion of the planets. But in both cases, the high dimensional measurement, the planetary motion, was explained in terms of a low dimensional latent variable. And that's the goal of nonlinear dimensionality reduction. And so basically Kepler's genius was that he figured out that the correct latent variable was indeed distance from the sun. It's a one-dimensional manifold. It's not a two-dimensional one like Ptolemy thought. And he actually figured out exactly the mapping G that maps from Z, the latent variable, to the measurements. So in fact, without performing any additional measurements, just by analyzing other people's data, he figured out the distance of all the planets from the sun to an amazing degree of accuracy. So I think this is really a triumph of modern science, the ability to make these inferences about latent variables from high-dimensional observed data. And the question of this talk is, can we use machines to replace these brilliant scientists? So we live in the era of big data. We have very powerful machines. Maybe planets are not a good setting because, you know, Kepler did it with only measurement of a handful of planets. It's not really that much. But think of an example like analyzing gene expression data or neuronal recordings, or even something like the preference of viewers on Netflix. It's very easy for us these days to get a tremendous amount of measurements, say recording many genes, and these measurements will be high dimensional. So we can measure, say, the expression data of all the genes in many cells, and we assume that these are actually factors of a low dimensional function, latent variable z. And so we can think of this artificial Kepler or artificial intelligence method, which will try to replace the scientist and look at these high dimensional measurements and try to recover the underlying low dimensional causes. Okay, so that's the big ambitious goal of this project, is asking whether machine learning, just by observing very high dimensional measurements, can recover the correct low dimensional latent variables that explain these measurements and the mapping from the low dimensional measurements to the high dimensional, from the low dimensional latent variables to the high dimensional measurements. So even if you had never heard this talk, but you've gone to the other sessions today, or you've followed the recent literature on machine learning, you probably have an idea for how to solve this task. And that is indeed what many people are doing recently. And the idea is to use some form of an autoencoder, which is shown here. This is from a paper that appeared in Nature 3 years ago. And the idea is we take the high dimensional measurements. In this case, these are many cells, say I think something like 80,000 cells. And for every one of them, we have the expression level. So every one of these cells defines a high dimensional vector of say 20,000 measurements. And we pass these measurements through an autoencoder, so a deep neural network that takes the high dimensional measurements, maps it to a low dimensional bottleneck, and then back up to something that is the same dimension as the input. And we train the autoencoder so that it reconstructs the measurements, but because it's forced to go through this low dimensional bottleneck, the assumption is that this will recover the latent factors. It will basically perform nonlinear dimensionality reduction for us. So here's a quotation from this recent paper in Nature. It talks about the representation here in the bottleneck layer. It should ideally represent the underlying biological processes or cellular states. For example, in the data set where snapshots of differentiating blood cells exist, the manifold view can show the continuum of differentiation phenotypes. So in some sense, this is my dream come true. We have an automatic method, an automatic machine learning method, which just takes a lot of high dimensional data in its input and discovers some other latent variable, in this case, the bottleneck representation, which ideally discovers something interesting scientifically. And indeed, in this paper, if you just look at this plot over here, in this case, they took 68,000 cells and they mapped it into this two-dimensional representation that was discovered by the deep neural network. And their argument, I'm not a biologist myself, is that this two-dimensional representation is very useful. So they say their method, which they call DCA, enhances biological discovery. So by looking at the scientific information in this low-dimensional manifold, they feel like they have discovered something about how the world works. And the problem that I'd like to talk about today is whether this method can actually work. And this is related to what is in modern machine learning called disentanglement. So let me try to formally define what disentanglement means. Suppose we're given these high-dimensional observations. Again, think of this example of many cells, and for every cell, we have a high-dimensional vector of gene expression data. And let's assume that this data, we know its ground truth latent factor. So we know the true Z. And so every one of these measurements is actually a function of some low-dimensional latent variable, Zi. And now we train a machine learning method, and it recovers another low-dimensional latent representation that we're going to call Yi. So think of that, for example, as what this deep autoencoder learns. So Yi would be the representation here in the bottleneck layer. And the problem of disentanglement is, can we guarantee that Yi is the same as Zi? So, of course, the machine learning method will recover something by definition, but how do we know that that something is the correct latent variable? Only if we know that it's the correct one can we say that the machine has discovered the laws of nature. Otherwise, it's just performing some form of denoising or cleaning up of the data, but it's not really discovering the true latent factors. Okay, so that's the task. We want machine learning to discover Y, which will be the same as Z, where Z is the true generative model of the process. And again, typically today in modern machine learning methods, this is done using regularized autoencoders. So we train this autoencoder to reconstruct the input, but we also add a regularization, an additional term to the loss, which is weighted by some parameter beta. And we hope that that regularizer will help us to discover the correct latent representation and achieve disentanglement, or in other words, achieve scientific discovery. And the starting point for our research is this recent work from 2 or 3 years ago, which shows that in some sense, almost all of these methods don't work, neither theoretically nor experimentally. So this paper is by Locatello and co-authors. It received the Best Paper Award at ICML in 2019, 3 years ago. And what they did is they have both an experimental side of this work and a theoretical part. On the experimental side, they just trained many models that are all of this form, and it evaluated them on a various number of data sets for which we know the true Z's. And again, we asked the same question that we asked earlier: is the recovered Y equal to the true Z? And what they show is, they phrased it very politely, but in perhaps less politically correct terms, they basically show that many of these methods do not work. So here's the exact phrasing from their paper. The disentanglement scores of unsupervised models are heavily influenced by randomness in the form of the random seed and the choice of the hyperparameter in the form of the regularization strings. The objective function appears to have less impact. So here's just an example of their results. The x-axis here is this number beta that I talked about. So the higher this number is, the more disentangled the output should be. And the y-axis is the actual disentanglement score, where 1 is the best and 0 is the worst. And you can see that there's basically no difference between when you look over all settings, all initial conditions. There's really no difference between the highly regularized solutions and the non-regularized solutions. They're all equally likely to give either a good solution or a bad solution. And they also showed, this was just experiments, but they also had a very nice proof that this is impossible. And I want to take you through the proof, just what I would call proof by figure, proof by illustration. Suppose we have the correct Z, and we know that it generates the high-dimensional data through some decoder, G, that maps Z to X. We can always apply some function Q that would map Z to a different Z, Z hat. And there's an infinite number of these, but the important point that they made is that we can also choose this Z so that it will preserve the distribution. So that's shown here. Here, Z is a two-dimensional latent variable, and it's assumed that it has a uniform distribution. So you see the values of Z lie uniformly span the unit square. But we can map it to another Z hat that also uniformly spans the unit square, like here. And we just add the inverse of Q to our generator. And we have another pair, Z hat, G hat, that perfectly generates X. So Z generates generates X, and we'd like to recover Z in this generator. But there is no mathematical reason that we will discover this Z and not Z hat, because both of these will have exactly the same reconstruction loss, because they generate exactly the same X's. And they'll also have the same regularizer, because the regularizer just looks at the distribution of the Z's, and they're the same in these two cases. So there's no reason that we'll discover the correct one, which is this one on top, or an incorrect one, which is the one on bottom. So really fundamentally, just this approach of using an autoencoder with these regularizers that look at the distribution of Z just cannot work to discover the true latent variables. So this is from their, basically the take-home message of their theoretical part of their paper. Disentanglement is fundamentally impossible for any deep generative model with a regularizer based only on P of Zi. So in this case, the regularizer said, we want the Z's to have a uniform distribution in the latent space. As long as we only have a regularizer of this form, it's impossible for us to discover the true Z's. There's an infinite number of possibilities that would be bad and have exactly the same loss in the autoencoder as the true Z's. So here is an example of a method that is not supposed to work according to this math, something called the beta VAE, which is an autoencoder and a regularizer with this beta, which basically measures the distribution of the Z's and compares them to some ideal distribution. And in the paper, they show that small values of the regularizer often give highly entangled results. And you can see that these are, what you see here are the heat maps of individual neurons. And so every one of these neurons encodes the data set is a bunch of spheres, blobs at different locations. And here every neuron, as a function of the location, has a very maps location in a very entangled way. There isn't a single neuron here that maps the X location, and there isn't a single neuron here that encodes the Y location. But with beta 150, they found these two neurons that do a very good job of mapping. Of one neuron represents the X location, and the other neuron represents the Y location. And so this is a success of this method. But the Locatello result says that this we cannot really explain the success in terms of the loss function that the method used, because for any value of beta, there exists an infinite number of highly entangled representations that will achieve exactly the same regularized loss as the disentangled ones. So in some sense, we were very lucky here to get this result and not a result that looks like this. So let me finish the first half of this talk, which is about really, there's hundreds. I sort of highlighted two papers, the beta VAE and this other method from Nature, but I just picked on these two, but there's actually hundreds of papers over the last few years that do something like this. They take high dimensional data, pass it through an autoencoder, and use the latent representation for scientific discovery. And if you take seriously both the theoretical and the experimental data results from the machine learning community, you realize that this optimism of using this method is unwarranted. There is no reason to believe that such a method can work. But I don't want to leave you too pessimistic. So in the second half of the talk, I want to talk about something optimistic that we can actually recover the laws of nature in some sense, using some additional assumptions and different types of algorithms, not deep autoencoders, but different types of machine learning algorithms. So our result is theoretical, and it's late in the day now. I don't want to go too much into the math. I'll just give you a high-level view of what our result shows, and then I'll try to show you some experiments that hopefully give you the idea of how our method works and what our results can prove. So we prove that there's two mathematical assumptions that we have to make. One is on the model, and the other is on the latent factors, and I'll go into them. And if these two assumptions hold, then unsupervised disentanglement is possible using a combination of two classical methods, which I'm going to talk about shortly. But really at the high level, what I want you to take home is that these are methods that are over 20 years old. They're not deep autoencoders. They're very different types of methods. We didn't invent these methods. We're just the first to point out that the combination of these two methods can solve the problem. But what I want you to take from at a high level is that these are very old methods and not deep autoencoders. They're very, very different, as you'll see in a little bit. Okay, what are the assumptions? This assumption is called local isometry, which is sort of a fancy name, but I'll try to explain what it means. Local isometry means that if we take our latent representation and change it by a little bit, we expect the high dimensional measurement to also change by a little bit. So let's think about images of cats, and let's assume that all these images are generated from just two latent variables, the color of the fur and the pose of the cat. So this cat was generated by choosing white for the first variable and this particular pose for the second variable. And so we'll say that the representation satisfies local isometry if we change the z's by epsilon, the image will also change by epsilon. That's the definition. If on the other hand, we can change z by a little bit and the image will change dramatically, that's a mapping that doesn't satisfy local isometry. Okay, so that's the first assumption. The second assumption is non-Gaussianity, which is, go back, sorry, which is again, we have to assume, as I did in the earlier experiments that I showed you, that these latent variable doesn't have a Gaussian representation, because otherwise there's always, because you can always rotate Gaussians and they remain Gaussian, you want to have something that's non-Gaussian as the representation. So these are the two assumptions. And then the methods are Hessian eigenmaps and FastMaxCA. So Hessian eigenmaps, you can find it in any package that does machine learning in Python. It's very, it's called HLOE. Usually in the packages, it's a method from 2003. And the way that it works is essentially using, again, I don't want to teach exactly how it works, so that you can program it after this talk. But just to give you a flavor, what you do is you take every point in the high dimensional space and you estimate a local PCA around that point. And then you essentially get this local PCA to construct what's known as a Hessian. It's a big matrix whose size is n by n, where n is the number of points. So if you have, say, 10,000 points, you'll have a 10,000 by 10,000 matrix. And then you find the eigenvectors of that matrix, and that gives you Z. So you see, it doesn't sound at all like training a deep autoencoder. It gets X's in as input and outputs Z's, but it does so in a way that is very different from training a neural network. And then this is an algorithm from 20 years ago. And actually, there was a proof in this paper by Donahoe and Grimes, 2003, that it's guaranteed to find the true Z up to linear transformation if local isometry holds. So this is the first algorithm that we use, again, an algorithm from many years ago. And the second algorithm is even older. It's called fast ICA. And fast ICA is essentially a method that solves the disentanglement problem for linear generative models. So if you have a generative model here that's linear, it takes z's and applies x's to them. If you tell this algorithm that you want to find the true z's, it can do so. And the reason is that any other linear track, it's also true, just like I talked earlier, that you can apply Q here and inverse Q here, and you get another generative model. But this will destroy will change linear, for anything that's not Gaussian, this will change the distribution over Z's, and the algorithm can pick up on that. And that's how fast ICA works. And again, it's guaranteed to find the true Z for the linear case, for the linear generative model case. Okay, so let me just recap. Our goal here is to try to discover the laws of nature using machine learning. And maybe the first thing we all think about is to train an autoencoder and look at the Z's that are discovered in the first two in the intermediate layers, bottleneck layer. I hope I've convinced you that's a bad idea, that there's no reason to believe that such a method will work. And then I hope I've given you some optimism that if our mathematical assumptions hold, and we're going to discuss whether or not that makes sense or not, we can make this work with other more classical methods that will recover the true Z's. And so we're optimistic that that can actually discover the true laws of nature. But let's see how this works in experiments. So the experiments, we're not going to have motions of planets here or recordings of neurons because we don't have ground truth for all these things. We're going to look at images. And the way we're going to work with our synthetic images using StyleGAN, which probably many of you have heard on. These days, we can generate very realistic images using a deep generative model that gets as input only two numbers. So in this case, all these images of cats were generated using a deep generative model that receives as input two numbers. One is the fur style, and the other is the pose. You see, as we go from left to right here, the pose of the cat stays the same, but the fur color changes. And if you go from top to bottom, the fur color is the same, but the pose changes. So we generated these ourselves, so we know what are the ground truth factors here. This is the first factor, and this is the second factor. And the experiments we're going to ask is we give a bunch of algorithms, just images like you see here on the right. Of course, they're not ordered in any way, just a bunch of images of cats, which were all generated from this mapping. So we know the true latent variables. And we ask, will the machine learning recover the true latent variables? So we ask machine learning algorithms to return us two numbers. Are these two numbers going to map indeed one to fur color and the other to pose? Or are they going to be some weird nonlinear function of these two numbers? If it's the first thing, then we say the method has succeeded. If it's the second, we'll say that it's failed. So we worked with a number of these manifolds. The simplest one are just squares at different locations, similar to what I told you about that was used in previous work. So this is a two-dimensional, the latent variables here are two-dimensional, the x location and the y location, and we give the algorithm just a bunch of squares at different x and y locations and ask them to recover these two latent variables, x and y location. We do the same with color of squares. Here, they only change in x location and the color. So again, there's two-dimensional latent variable, and we want to see if the machine learning can discover them. And we have 6 other manifolds, which were taken from StyleGAN. So this would be faces of different poses, cats, horses, cars, kitchens, bedrooms, churches. Get the feeling. In all these cases, we know what the ground truth is, and we're just going to give the algorithm a bunch of these images and see whether it recovers up to some linear transformation the true generative model. So what we want to look for is, we're going to look at individual neurons in this representation and see whether there's one neuron that encodes the first latent variable, true latent variable, and another neuron that encodes the other. So what you want to look for are these heat maps that should be axis aligned. Here we have one neuron that encodes the first latent code and a true latent variable, and the second neuron encodes, doesn't care about the first number and cares only about the second number. So this is an example of a success. All of these are examples of failures. And we also have a numerical way of measuring success in addition to this visual way. So let me just show you one result. This is on the Katz manifold. Here, this is PCA, which is a linear dimensionality reduction technique. Not surprisingly, it doesn't work because there isn't a linear mapping that allows you to go from these images of cats to something like fur color and pose. So we don't see it encoding the true generative factors correctly. And this is what happens if you just train one of these deep autoencoders with a bottleneck of size 2. And the funny thing is, it perfectly reconstructs the images of the cats, but the representation is totally jumbled. There is no encoding here of the true generative model, true generative factors. It recovers a two-dimensional encoding. And so if we were publishing a scientific paper, we would maybe show this kind of mapping and say that we've succeeded, but in fact, we have not succeeded. Or here, we've learned some strange nonlinear function of the true latent factors. And this is true. We tried all sorts of regularizers as well. And similar to what Locatello et al. Showed, these methods just don't work. They don't succeed in recovering the true generative model, even though this data is synthetic and we know that it was generated from as a nonlinear function of 2 dimensions. In our method, which is of course guaranteed to succeed when we have infinite data and all sorts of assumptions hold, also works in practice and recovers. So one of the neurons in our setting recovers the first variable and the other one encodes the second variable. And we can also measure this numerically, and it's basically, we get results that are close to perfect, and all these deep autoencoder methods get results that are not any better than PCA, and PCA is pretty bad, as I showed you earlier. So this failure of the deep method is not surprising. It was shown already in previous work, but it also fails on our data. And I think what's interesting is that following our mathematical results, we also showed that our method succeeds. And we can also do interpolations, which is another way of showing that our method succeeds. In our method, when you change one of the numbers, so you take, say, this cat, and you just change one of the numbers that the method recovers, it just changes the pose and keeps the fur color the same. And if you change the other number, you change the fur color and keep the pose the same. On the other hand, if you take one of these deep autoencoders and you change one of the numbers, you change both the pose and the color simultaneously, indicating that the method is entangled. It has not succeeded in finding the right thing. Okay, and of course our method has limitations. I don't want you to go home and think that this method solves the problem of disentanglement, and we're working on trying to make it better. And just to get back to what I was talking about in the beginning of this talk, our algorithm only works with a particular kind of assumption, and we have to think whether these assumptions are realistic in the context of scientific discovery. So let's go back to Kepler and think, could we replace Kepler and Galileo with machine learning? So I hope I've convinced you that if we took their data and passed it through a deep autoencoder, chances are it would not find the correct latent variable, the distance from the sun, and Kepler's laws. And our method would succeed if this satisfies a local isometry, and I think it is actually realistic in the setting that if you local isometry means that if you change z by a little bit, x will change by a little bit, and I think that is actually true for the case of Kepler's laws. a small change in the distance from the sun will change the planetary motion by a small bit as well. So I think at least for some scientific discovery settings, our assumptions are correct, but still our assumptions are in the setting of infinite data, unlike the case of planetary motions where they worked with a handful of planets that they measured at the time. Okay, so let me conclude. Really the question that I wanted to address in this talk was, can machine learning discover the laws of nature? In the first part of the talk, I talked about the recent optimism about deep generative models, and I hope I've convinced you that I believe that this optimism is unwarranted. These methods based on autoencoders should not be able to discover the correct latent factor. They can still be good for other things, but in terms of scientific discovery, they're not a useful tool. Then I told you about our theoretical result, which is that under local isometry and on Gaussianity, unsupervised disentanglement is provably possible. And then I showed experiments which showed that methods that assume local isometry indeed succeed while baseline autoencoders fail. So overall, I see this as a first step towards the much more ambitious goal of trying to discover the laws of nature from high-dimensional observations. Thank you. Happy to take questions.